So our, let me say, target is the surface of the materials, that is the surface of a component. As we will see later, we do have many important technologies which must be known by advanced, how to say, engineers. But first, before going inside these technologies, let's answer to the question, do we have any characterization techniques which allow to us to understand if our surface modification has reached the goals that we want or not? Why I make this question? Because technologies, lab scale testing that we do have available, and we do have it, for the surface characterization are slightly different from those which are used to characterize the behavior, the performance, the properties of a bulk or a monolithic materials. So this is just a very quick, let me say, review on the technologies which are usually used, not all, the most important, for the characterization of a surface. And we could be asked, for example, to answer to the question, which is the general state of a surface, the shape, the appearance, which are the mechanical properties of a surface, such as modulus, such as resistance, for example, yielding strength or toughness, or eventually residual stresses or residual strains, which is the composition of the surface in terms of, for example, elements which are present or phase distribution, which are defects that can pre-exist or which can be eventually induced by the modification techniques, for example, changes in shape, in mechanical properties, in chemistry, or eventually defects that we already know now, which are called cracks, so very important for fracture mechanic topics, for the lifetime when, for example, we do have fatigue, as we have seen last time. So one important techniques which is available on the lab scale is devoted to measure, so this means with figures, with numbers, the surface topography. And the most common industrial and also at lab scale method is to use, in order to have an idea, a numerical idea of the surface topography, the stylus profilometry. That's quite simple, conceptually speaking, because we do have a shell point, which is the important part of the instrument, which is dragged across the surface, and up and down movement of this point, they are recorded. So we can have an idea of the topography on the y axis and on the x axis. And we should be aware that since usually the scale length, the reference of the y axis are much more smaller of those on x axis, especially if we are thinking about to real component, to industrial component, to engineer component, we should pay attention to use the proper vertical and horizontal scales. Otherwise, we could get, for example, just a profile like those it is reported in the first drawing that is here, which tell us nothing. But if you see, if we change the scale, then we can approach the real situation, which describes on the y-axis the topography of the surface, which is important for us in order to get what? For example, one data is the so-called average roughness, which is called also as RA. And this is a very simple mathematical, let me say, operator, given by an integral on the modulus like this, on the up and down movement of the point on the y axis, and it represents just the arithmetic mean deviation of the surface height from the mean value. That's the definition, okay? So this means that we are putting to a certain distance from x equal to 0, let me say this average value, with, and this is the meaning of this integral, with the hypothesis that the sum of the areas above and the sum of the areas beneath, that is under this value of RA, they are equal. We have also the mean square roughness, which is called RQ, which is defined again by an integral, like the usual definition that we have in the mean square. And so these two figures, RA and RQ, they give to us an indication of which is, let me say, the topography of our surface on the y axis. They are overall parameter, so they do not give to us detailed information about the distribution of the heights, because they give to us just the figures, just a number, as well as they do not give to us information about length scale in surface or eventually the existence of possible potential anisotropy. And for this, we need more let me say, fine techniques. But as you will see in a moment, each time we are going to have detailed information, for example, distribution of heights, the number of data which are collected by the instruments are so high because the scales are different between y and x. And so usually we do have this information for very small parts of our surface, and we need to repeat it if we want to have an overall overview of the surface itself. Here, for example, we can think to use, in order to have more detailed information, surface visualization methods like optical methods, for example, based on microscopy, giving us results like this one, for example, by using also profilometry, which is based on the use of a laser scanning techniques. These are just some two examples. Or we can use scanning electron microscopy or stereo pair imaging based on the microscopy, which has an excellent depth of field. But remember, we are working usually with scanning electron microscopy with magnifications which are up to, that's the maximum limit, 10 to 5. And so this means that the area that we investigate, according obviously to the magnification that is used in order to run the instruments, is a very small area. And so typically, you see here, for example, we can have some information on the basis in order to find a compromise of micron, 10th of micron, not meter, unless we prepare a lot of samples and then we make this analysis many times. The atomic force microscopy is another instrument. It is it's known as AFM, which in the, let me say, more usual configuration is based on the use of a very fine tip, this one, which is positioned on a cantilever beam, this one, which is going to run on the surface we want to characterize. And then by using a photodiode and by using an impingement laser, we can record the up and down movement of this very fine tip, which is mounted on the cantilever. And this is a quite detailed. It is a little bit similar to another techniques, but the so-called scanning intelligent microscope. But AFM is more important for this. But have a look to some images which can be get by using AFM. You see here, this is an area which is investigated. Look here to the dimension, 3 micrometer, and the same more or less applies also on this axis. And we can go also up to 10th of micrometer. You see here, it's an example of characterization of a braided ceramic surface after wear, but we are not in the range of, let me say, meter or 10th of centimeter. So each time we get detailed information, we need to refer this detailed information to very small areas. And so we need, as we said before, to repeat this analysis in many points of our surfaces if we want to understand if that situation, I mean, one situation measured in one part can be the same expected in the other parts. For what it concerns the mechanical properties, that's a very interesting and important topic, because usually we can have sensible differences in mechanical properties on the surface, depending on the surface engineering methods we are going to use, with respect to the bulk materials, even though we are not making a coating, but we are just arranging some surface modification. For example, then I will tell to you which are the most important. For example, by changing locally, by diffusion, solid state diffusion, the chemical composition of the surface. So if we want to understand the mechanical properties of the surface, we must be sure that our techniques are focused just to characterize the surface response and not the bulk response. And since the variation in surface properties can be in a depth also localized in very thin layer, which can be also the length of 1 micrometer, you can understand as if we, for example, want to know which is the Young modulus, let's say in this way, of the surface, we cannot use the standard tensile testing that we use in order to characterize the bulk materials and then have the classical stress strain diagrams, because the answer of the surface in that case is hindered by the answer of the bulk materials. And so we need techniques which can evidence the response of the surface. And one of the most common way, in order to have an idea, but also measurements, accurate measurements of surface mechanical properties, is to refer to the equipment that we use to make harder measurements, common harder measurements, with what is hardness with a load P on the surface. Then we can experience elastic and plastic deformation on the surface to a certain depth that depends on the indenter shape and size and on the load applied. So these are two parameters which are very important for us. And after having experience a plastic deformation on the surface, we are going to characterize with different formula depending on the hardness testing which is used, because it can be Vickers, it can be Rockwell, it can be a Knupp, it can be Shore hardness, but more or less with different formula, the concept is quite clear, because the hardness is defined as the ratio between the applied load and the impression area, that is the plastic deformation which can be measured and evidenced. And usually for a series of materials, especially for metallic, very well known metallic alloys, hardness and yield stress of the materials, which are always in relationship because we have higher hardness value if the plastic deformation is lower. That means the impression area is lower. That means that the yield stress is higher. So we have a direct correlation between hardness and yielding strength of the materials. For some materials, especially metallic alloys, there is a theoretical relationship which can be derived for which the hardness is equal to 3 times the yield stress of the materials. Many times, and generally speaking, it is written 3, which multiplies a coefficient beta, which is different for different materials, but in any case, multiplied by the yielding stress. So by other measurements, if we have in mind this correspondence, we can have an idea and also measurements of the yielding strength of the materials, in this case of our surface. But what we must be sure that the depth of penetration of the indenter, that is of the plastic deformation, must be localized essentially to the very thin layer if we want again to have an answer which is the answer of the surface and not the answer of the bulk material. And so this means that we need to use proper shape and size of the indenter, but essentially proper load which are applied. And so in hardness, I remember to you that we can have the distinction between the so-called macro hardness, in which usually or generally, that depends also by the standard we are going to use, by the form of the indenter, we have applied loads by means of the indenter which are higher than 1 kilogram. We can have micro hardness in which loads can experience values which are between 10 grams 1 kilogram. We can have also the area of the so-called nano hardness in which the loads are very, very low, because they are 1 micronewton, that is 10 to minus 4 grams. And so what we can expect is that if we want to have the surface response, obviously we cannot rely on macro hardness because the loads are so high that the contribution of the bulk is quite relevant, since the penetration depth of our indenter is quite relevant. Sometimes we can have an idea of the surface response by using micro hardness with loads which are of the order of maximum 10 grams. Most of time, especially for very thin characterization of the surface, we need to rely to nano hardness measurements with dedicated instruments, which is called also nano indenter. And hardness is also, I will be back in a moment on the nano indenter. Sorry, let me say also this, that hardness value, when well measured, they are also very interesting because there are, and they were developed, some theories which must be, let me say, used with a proper attention, by which making our test and putting, depending on the applied load, the surface in the condition that at the edge here, for example, of the indentation, some cracks are developed, okay? It is possible, this is a theoretical, there are many theoretical models, many of them give good results, to have an idea, depending on the length of the cracks which have been generated at the tips of the indentation, to have an idea and to calculate the fracture toughness of the material. So these techniques of hardness measurements, when properly executed, can give to us indication about hardness, that's okay. Indication about the yielding strength of the surface, indication about the fracture toughness of the surface, and they can, if properly carried out, give to us also indication of the Young modulus of the surface. Why? To do this, we need to use the nano indentation. So the nano indentation is essentially, let me say, a standard indentation, but carried with a very, very sophisticated instrument, which is able, usually in the most known configurations, which is able to detect the displacement resolution of what? Of the tip, okay, of the nano indenter, which is very, very low. You see here, 0.02 nanometer, with a maximum indentation depth, when we use the maximum load, which is of 500 microns, so half millimeter. But if we use very low loads, we can go also in terms of depth of 100 or 50 or less, 1 micron, for example. So that's characterizing exactly the response of the surface. And this is a technique which is used by, let me say, recording at the same time the applied load and the penetration depth of our tip. So if we put on a diagram, let me say, the applied load, which is in this case a load which follow a sort of increment line. Meanwhile, we are applying the load. And here we put, for example, the penetration depth on the surface. We have a loading curve, okay, which can be recorded. Then at a certain time, when we remove the load, what we can expect to have? We can expect to have an unloading curve, okay? And what we can expect to have in terms of depth of penetration. The depth of penetration of our tip give to us both elastic and plastic deformation, since after this testing technique, the impressed area still remains on the surface. And so when we are unloading, if we are going to record the unloading curve, we can expect that the materials, in this case, the surface behavior, is something like those we have already seen when we were discussing about the stress strain diagram for a bulk materials. So we have the elastic recovery. So the elastic deformation is recovered because that's an elastic deformation. But we do have also a plastic deformation that is a not recoverable deformation, which still remains on the surface, so giving to us the final impressed area. And by measuring the elastic deformation recovery, we can have, obviously, this is a concept that we know, measurements and indirect measurements of the Young modulus of the materials, because the elastic deformation depends on the Young modulus of the materials itself. And so by using the non-indentation techniques, when we want to characterize the surface properties in terms of mechanical properties, we can have a measurement of the Young modulus of the materials, apart from the hardness, obviously, the Young modulus of the materials. If we do have a suitable relationship between, numerically speaking, between hardness and yielding strength of the materials itself, we can have an estimation of the yielding strength of the surface. If we use a model in terms of presence of crack propagation on the crack on the tip of the impressed area, we can have an estimation of the fracture toughness of the materials itself. And thus we can have three of the most important parameters which are able to characterize the mechanical properties of the surface itself. You see here, we cannot use any CT specimens like in bulk materials to have a measurement of the fracture toughness. We are not going to use a standard tensile test in order to have an idea of the Young modulus or an idea of measurements of the yielding strength of the materials itself, because this testing, the last I have mentioned, they are suitable for bulk and they are not suitable for surfaces. But we do have, that's the message, at lab scale, instrumented instruments which allow to us to measure the surface properties before and, if you want, after the treatment to which the surface is eventually subjected. And so if we enter in the area of the surface engineering methods, we can say, in order to have a classification, that any surface can be engineered by following two different lines. One line is just to modify the surface itself, for example, without any change in chemical composition of the surface, or with changes in chemical composition of the surface. And in the first case, no change in composition. For example, we can rely on the variation of surface properties. I will give to you some examples by using mechanical treatments. This does not imply that we are going to change the composition. Instead, if we are in the surface modifications approaches with change in composition, for example, remember the thermochemical treatments which can be used, like carburising, for steels. In that case, we are changing the composition of the surface through diffusion of carbon. Then, in some cases, we can have temper, as you remember. But we are not introducing in these classes of the surface modification, let me say, an additional interface between our material M and the final surface which has been treated. This is what is going to happen when, instead, in order to modify the surface response, we are going to use coatings. Okay, and then in the area of coatings, which will be the area I want to discuss with you in detail, we can have standard coatings techniques like electrolytic-based methods, or, for example, all the area which includes the fabrication of thin or thick coatings by relying on the thermal spray methods, the ones that we have mentioned many times, but we will see better now for the fabrication of thermal barrier coatings, for example, as well as another very interesting and important class of techniques are in the area of thin coatings based on vapor deposition method. And here we do have two broad classes, the so-called CVD-based process, chemical vapor deposition processes because they are many, as well as in the PVD processes, which are physical vapor deposition processes. But to give to you, let me say, an overall view, what are, just to remember, something that you should have seen, but it's worthwhile to be mentioned again. What are the main techniques which are used in the area of surface modification without coatings? We mentioned mechanical methods. Mechanical methods, for example, are pinning and blasting. And in this case, what we do, we use a controlled impingement of short or abrasive in order to modify the surface. These techniques, for example, the so-called shot peening, is very important for bulk materials, metallic materials. No coatings are involved, because by using this technique, we can work harden the surface, and we can put our surface in a final state where residual compressive stresses are on the surface itself. And this is very, let me say, useful, for example, in order to improve or to increase the fatigue resistance of the metallic base alloys. Since if we have compressive residual stresses on the surface, and considering that most of fatigue rupture are starting from defects on the surface, which propagates inside the bulk materials, if we put compressive stresses on the surface, we are putting, let me say, obstacles to the propagation of cracks, which, as we have seen and told many times, they can propagate if they are subjected to a tensile stress, not to a compression stress. Think to the mode 1 of fracture propagation, for example. So this is quite usual techniques, which is used, let me say, in standard surface modifications without any change of composition of the materials, just putting work hardening on the surface and then residual stresses on the surface itself. Transformation hardening, that is thermal treatment, are other possibilities in which we do not change the composition, but we can change, for example, the microstructure on the surface. And this is made by, essentially for steels, by using flame hardening or by using induction hardening. That is to making a thermal treatment, for example, surface temper, for example, when obviously the composition, the starting composition of the materials put the steels in the area of the steels which can be tempered. We can have also laser hardening of the surface, and in this case, laser can also, that depends on the power, be able to determine incipient melting of the surface itself, so localized melting, and thus controlling the cooling time. We can develop tailored microstructures just on the surface, not changing the composition, but changing the microstructure. That means changing all that properties which we have defined as extrinsic properties of the materials itself, in this case, extrinsic properties of the surfaces, because remember that the extrinsic properties are those which depends on the microstructure of the materials itself. So, for example, this is one example you see here of an aluminium, silicon alloys, as cast, that is, as fabricated, and after, we are talking about the surface, after laser remelting just on the surface. You see, just having a look to the picture, how the microstructure is very different. And this, for example, in this special case, resulted in a double value of the hardness of the surface itself, because we have changed the microstructure. Remember, hardness is an extrinsic property because it's linked to the yielding strength of the materials itself, through the simple formulation we have seen before, and the yielding strength is an extrinsic properties of the materials. That is, it's depending on the microstructure of the materials itself. And then we do have all the area of the so-called thermochemical treatment. Also these, they have been developed and they exist essentially for iron-based alloys. And in this case, we can have diffusion, for example, of interstitial elements like carbon or like nitrogen, or in some cases like boron. Or we can have also solid state diffusion, which does not rely only on the interstitial defects, let's say, that is, elements which are put on the interstitial free space of the lattice, but also by substitutional mechanism, like it happens, for example, with the use with some alloys, iron-based alloys of chromium. But carburizing is inside this area, and now we are entering in this area in the surface modification, which does not imply the use of coatings. So we are not in the area of anodizing, thermospraying, and vapor deposition techniques, no coatings, but we are modifying the surface, composition, chemical composition of the surface itself. And this carburizing, you remember, is good. It can be declinated in different ways, in the sense that we have a gas carburizing, a case carburizing, a vacuum carburizing, a plasma carburizing, etc., etc. But essentially, it is based on the solid state diffusion of carbon, which we are able also to model, because remember the Fick law of the solid state diffusion, which we know also in terms of mathematical solution to make some calculation, and the diffusion of carbon to a certain depth, which can be calculated and controlled from the top of the surface, give rise, in this case, to the presence, due to the size of the carbon atom, of carbon in the interstitial elements. And then, as it happens, just to remember to you, for what it concerns iron-based alloys, the carburizing is, let me say, one step of the final treatment, which is devoted to an increase of hardness of the surface itself, because after carburizing, usually we make a temper, a surface temper, with a possibly with the formation of martensite on the surface, which gives to us a very hard final surface, just for the depth, which is desired according to how we have performed the carburizing process, that is, according to how we have designed the diffusion of carbon from the outer surface inside our component. We can have also diffusion of nitrogen. In this case, if we have diffusion of nitrogen enriching by the Fick law, the difference between carburizing and the diffusion of what is happening, okay, of nitrogen, is that when we use nitrogen on iron-based materials, we do not need the further step of quenching of temper, because with diffusion of nitrogen, there is the direct formation of iron nitrides, okay, which are hard, very hard compounds, able to give to our surface the increase of hardness which is expected. So we do not need to temper if we just use solid state diffusion of nitrogen. We can have also the mixed situation, which is the so-called nitrocarburizing, in which we make temper, because together with the formation of iron nitrides, we have diffusion of carbon, and then we can have, after temper, the formation of the martensite. And also in this case, we do have a modification of the surface chemistry, because it is enriched in nitrogen or in carbon or both. Another example is boronizing, which is again based on solid state diffusion, in this case of boron. with the possible formation of iron boride layer, which can be two different forms. That depends on the stoichiometry on the diffusion process. Also in this case, we do not need any temper, because there is a direct formation of iron boride, which are very hard compounds. You see here, for example, by using a standard Vickers denomination of hardness, we can reach 1,500 kilograms per square millimeter in terms of Vickers hardness on the surface. And if we compare with one of the most, let me say, hard, simple, obviously, that is most hard in terms of simple oxides, that is silicon oxides, you see here how the value of 1,500 is higher than the maximum value of 1,200 for silicon oxide. And I just remember this because this is one of the most common materials which is used to have abrasive wear. Okay, so it's a good reference for understanding what is going to happen. This is an example of a microstructure of a layer boronized, which is extending in this case for something which is around 100 microns. And this is the reason because these 100 microns, this is the reason because we can think to use, in this case, for example, standard Vickers micro, not nano, hardness, because the penetration of boron and the formation of iron borides allow to us to use the standard Vickers testing micro hardness testing with, for example, 100 grams of loads and resulting in a depth of the indentation which is not essentially affected by the bulk materials, because the depth is still inside the surface layer which has been treated. If we go to, and if we move to the other class, that is the class in which we have and we rely on the formation of coatings, one, let me say, area which is quite known, technically speaking, is the so-called area of metallizing of the materials. Essentially, these techniques are used again on metal-based alloys. For example, chromizing is something which is well known, the so-called hard chromium coatings obtained by electrolytic procedures give to the surface very sensible value or very high value of hardness itself. We can have, for example, the possibility of have that's very, very tough in the sense that it is not so diffused. But it has been studied for many years, the so-called ion implantation techniques, in which we implant ions on the surface. And this has been made essentially by implanting nitrogen, or by implanting titanium, or by implanting chromium, in order to increase the hardness response, and that is the abrasive wear resistance of the materials itself. And that is, it has been made also onto polymeric materials, but it's a sort of niche, not so used for common industrial components. And so here I have what we have seen, that all these methods which we are discussing are essentially devoted to the treatment of steels, essentially for the steels, each having characteristics in terms of processing temperature and in terms of depth. So just to have a panorama. Coatings instead, standard, I would say standard coatings, plating, I was referring to that before, typical chromium or nickel on steels, by using electrolytic-based methodologies. That is, we do have an electrolytic chemical bath in which, for example, we do have chromium ions which are reduced and then deposited on the surface, thus giving a coating itself. Another technique, which is quite well known also for commercial application, is anodizing, as those is, for example, developed for aluminum-based alloys. In this case, the aim is to favor the formation of an aluminum oxide on the surface. That is the passivation mechanism for the aluminum alloys. Thus, if we are going to put on the surface of our aluminum alloys a very thin layer of aluminum oxide, that is a coating. And this can be done also, by using electrolytic-based methodologies, okay? And they are very common for components, not essentially for high-performing components, but in order to increase, for example, with hard chromium, the wear resistance of the surface, plating, the first one, or with anodizing on aluminum alloys in order to increase the corrosion resistance, electrochemical-based corrosion resistance of aluminum alloys, since as it happens in the stainless steel case, if we put a very thin film of oxide on the surface of our aluminum alloys, that oxide is not an electrical conductive materials, and thus the electrochemical-based corrosion processes can be suppressed. We have also, in this case, other techniques which are essentially for steels, and they are the so-called overlay well coatings, in which we are not making a welding between two components, but we are reporting on the surface of our component fused metals, as in the case we are going to weld something. And this can be done, for example, by using standard welding techniques like MIG, TIG, oxyacetylene, with the deposition of millimeter thick layers on the surface in order to improve the hardness, and thus essentially they can be made, let me say, by using manganese-based austenitic steels or martensitic steels, or in some cases like this, ceramic materials, that is materials which are made by a ceramic and metallic phase. And also these can be met, but essentially for industrial engineering, not for high-performing aerospace engineering functionalized components. So they must be kept in mind that in the sense that can be also met in some of your experience. But I want to go instead in the most important coating, which are those based essentially on physical vapor deposition methods, on chemical vapor deposition methods, and on thermal spray, which are those essentially used and widely used for a very high-tech surface engineering procedure. And let's start with the thermal spray. I think just with the fourth slide, then we will continue to discuss in the next meeting. And just remember what is a thermal spray process. What is a thermal spray process, which is the basis of the thermal sprays technologies, which are many also, not only one. To the thermal spray processes, just to remember to you, they belong the air plasma spraying that is used, for example, for the fabrication on turbine four-stage blades of the thermal barrier coatings made by partially stabilized zirconia. To the thermal spray process, it belongs also the high-velocity oxygen fuel technology, the HVOF, which is used, again, just to say, to remember one example we have discussed, for the fabrication of the bond coat, metallic-based bond coat in a thermal biocoatings, again, on the fourth stage blades of high-performing engines or in the combustion chamber. Okay. Conceptually speaking, it's a simple process, but in the operative part, they are processes which needs a lot of experience and a lot of attention, because they can be controlled. I mean, the final results can be controlled by a number of parameters, which can be in some configuration up to 30. And so we will discuss which are the most important controlling parameters in terms of quality of the coatings, but the basic procedure is, let me say, quite simple to understand, because we do have in a thermal spray process essentially four sections. The fourth section is an heat energy source, in which a heat energy source, which is usually confined inside a gun. So it's a confined area in which we generate heat or we generate energy. Then we do have inside this confined area in which we do establish heat, a material feed. Usually, not exclusively, this material feed is in the form of powder. At the same time, together with the material feed, which will be gas transported if they are powders, we have also other gas supplies, which can be, that depends on the technology, gas mixture, or in some cases, not for the cases which are interesting for us, but that's the general, let me say, situation, it can be air. What is going to happen is that these materials, which is feeded inside our confined region of space where it can meet heat or energy, is thus melted. And then through the fact that there is an insertion of gases which are flowing, due to the fact that our gun, it has a section of exit, the particles which are heated, they must be melted, they are also accelerated. So they come out from the gun having a temperature profile and a velocity profile, and they give rise to a spray pattern. Okay, this spray pattern of molten particles is addressed towards the surface that we want to coat, on which we want to fabricate our coatings. This gun can be controlled by a robot, which can be a programmable unit, and thus it can follow also very complicated profiles in order to make coatings not only on a flat situation, but also for shape and sizes which are very different from flat. This is the basic scheme. And according to this basic scheme, I will discuss with you this next time. I want to just close to this one. That we can have the possibility to generate our heat or energy source inside the confined area of the gun by using a combustion procedure. So we need to have inside that gun feeding of fuel and feeding usually of oxygen, not air. And to these classes of thermal spray processes, it is given also the name of thermal spray processes by gas. In this area, we do find the high velocity oxygen fuel process, the one I mentioned to you before for the fabrication of the bond coat or thermal barrier coatings, but we do also find other technologies, okay? So the thermal spray by gas is not only coincident with HVOF, even though for us, this is the primary technology, and so we will discuss this one. The second possibility, and look at this is a classification according to an international German standard, okay, is to generate our head source not by a combustion, but by an electrical gas discharge. With a formation, for example, that's a possibility of a plasma. And here we do have the plasma spraying technologies, that's a plural, not singular, as well as we can have also other ones, arc wire spraying, but for us, this is the important for our application, which can then be subclassified, if you want, according to the characteristics of the environment in which the spraying process is performed, because it can be performed, the spray process, by plasma in an environment where we have established a vacuum, and this is called also vacuum plasma spraying, or in an environment in which we do have the standard atmosphere, and this is called atmospheric plasma spraying, or that's very niche case, or the other one is the case in which we do have, for example, a closed chamber in which we put a pressure which is higher than the atmospheric pressure, and in which we can have also inert environment, and this is the area of the high pressure plasma spraying. So these are the topics on which I want to focus more your attention, essentially on the HVOF and on the plasma spraying technologies. And from this, we will start in the next lecture, giving a short comment, because this is a general table for all the spraying processes on this, which are the most important processing parameters, which will be then better defined depending for the influence if we are talking about HVOF or we are talking about plasma spraying in the various forms which is available to us. Okay, I think that for today is all. They are 1 o'clock. So if you have some questions, I'm here. That's not the case. So have a good weekend, and we will meet again next Monday.